Hi, this video is on things like specific heat and the molar capacity for heat. And we're following Young and Freedman's University Physics in the 17th chapter. And this is a section titled Quantity of Heat. So to start off with, from the number of times they mention it, it's pretty clear that Young and Freedman want us to distinguish temperature from heat. So temperature is a measure of a physical property. I have a temperature, which probably is about 98.6 degrees Fahrenheit. I think that's about 37 degrees Celsius. I have a temperature. This pad of paper has a temperature. This room has a temperature. And the temperature has to do with things like the kinetic energy of the molecules in this room, how much they're moving around on a kind of atomic level. That's temperature. Heat is something different. I don't have a heat. Heat always refers to a transfer of energy from one body to another because of temperature difference. So there is a heat exchange between my body, which is 98.6 degrees Fahrenheit, and the room, which is, let's say, somewhere in the 70s. And so I am giving energy to the room, and if I touch this, pad of paper, my fingers are transferring heat energy into the paper. Everything, eventually evens out, a la the zeroth law of thermodynamics. So temperature is the property of something. Heat always has to do with a transfer of energy because of temperature difference. Now, how do you change temperature? Well, you can change temperature by a heat exchange, like by holding this. This will become hotter. You can also increase or change the temperature by doing work on something. So let's say that I want to dissolve sugar in some tea, and I stir and I stir and I stir and I stir. As I stir, that tea, it's going to get a little bit hotter. Probably not a lot, but a little bit, because I'm doing work on it. So there are two ways to change the temperature of something. You can do work on it, or you can have a heat exchange. So that's the difference between heat and temperature. What are the units of heat? Well, the one unit of heat that we hear about is the calorie. A calorie is the amount of heat required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. And I imagine, I don't know the full reasons, but this seems like what a bizarre temperature range. Well, we know that like from 4 to 0 degrees Celsius, water does some crazy things. Like from 4 degrees to 0, it actually expands a little bit, which is great. Talked about it in the previous video. But it probably makes that smaller range not a good place to come up with the standard for a calorie. And so 14.5 to 15.5, I'm sure there's a reason it's so odd. They've standardized it in a stretch of a temperature change that's fairly regular and normal. Okay, now I'm on a diet of sorts. I'm trying to watch my calories. I'm supposed to only eat about 2,080 calories a day, according to my FitnessPal app. But the calories we're talking about there is not the calorie up here, but a kilocalorie, or 1,000 calories. Okay, there's another unit called a BTU, which you might hear in relation to air conditioners and that sort of thing. A British thermal unit is basically the amount of heat it takes to lift 1 pound of water 1 Fahrenheit degree. So you might hear that occasionally. Now, in terms of international units, the calorie isn't actually the standard unit of heat. The standard unit of heat is the joule. 1 calorie is 4,186 joules, and I think some change. But anyway, so the joule is actually the standard of heat. Remember, we did joules when we talked about work. So force times distance is work, and so that's 1 joule is a Newton meter, I believe. And so there's a relationship between the joule as it relates to heat and the joule as it relates to work. And you saw that in when I said that temperature can be changed by doing work on something or by heat exchange. So there's a relationship between heat and work here in terms of the joule. But the joule is the standard physics unit. And so if we did 1 over this, we would get how many calories there are per joule. Okay, now 1 BTU is 1,055 joules. Glad we settled that. Who knew? Okay, so the specific heat of something. Now, so let's say we are raising a substance by 1 Celsius degree. So the amount of heat it takes to raise 1 kilogram of a substance by 1 degree is proportional to the change of temperature, and it's proportional to the mass. And so we could set up a little equation that the energy required, the Q, the energy required is mc delta Q equals mc delta T, where m is the mass and delta T is the temperature. So this C here is a constant, and what is that constant? It is the specific heat. So C is the specific heat of something. Water, the specific heat of water turns out to be 4186 joules. Actually, it's not, I forget what the units of specific heat are. It's not just joules. So the constant C is called the specific heat. And the energy is positive when heat is going in. So if something is if you have an endothermic reaction, Q will be positive, and Q is negative when heat is going out. So there you have it. And of course, that relates to whether delta T is positive or negative. Delta T is positive when the change in temperature, when I'm gaining temperature, and so the Q is positive. If I'm losing temperature, losing heat, or my temperature is going down, change in temperature will be negative, and Q will be negative. Okay, so that's the specific heat. Q equals mc delta T is the formula to remember here. There's another thing called the molar heat capacity. So the specific heat has to do with grams, calories per gram, as it were. The molar mass has to do with calories per mole. And here we get back into our chemistry. You may have had a chemistry class, and if you have, you've probably already covered molar mass by the time you've gotten to this part of physics. Molar mass is basically the mass of a mole of a substance. A mole here is not a little creature that is annoying and eats your carrots and you need to get them out of your garden. That's not the kind of mole we're talking about here. A mole is 6 times 10 to the 23rd amount of stuff. And so it could be 6 times 10 to the 23rd atoms. It could be 6 times 10 to the 23rd molecules. But basically, a mole of something is 6 times 10 to the 23rd of it. And the reason why we do that is because, let's face it, atoms are small. And this is a big number here. And so if we had to count atoms, we would be using ridiculously large numbers in chemistry. And so Avogadro, I believe it was, said, well, let's basically come up with a collection of a large amount of atoms or molecules that will help us in our humanity to be able to, maybe God thinks in terms of individual atoms or individual quarks, but we as humans, since we're so big, compared to the atom, we think in terms of moles, which are collections of stuff. So the mass of a mole of a substance is the mass of 6 times 10 to the 23rd of it. And you can usually find it. Now, it's not always at the bottom, so I looked at a few periodic tables. Some periodic tables don't even have the molar mass there. They just have the atomic number. The atomic number of an atom, of an element, is basically the number of protons in the nucleus. The mass number is the number of protons plus neutrons in the nucleus. And so that's often written in a periodic table in the little box that has the element. Sometimes it's the bottom. Sometimes if the two numbers are on the side, it's the top number. So it's the bigger of the two numbers. So whenever you have two numbers, in the box of a symbol for an atom, the bigger number is the molar mass. The smaller number is the atomic number, which is the number of protons. Sometimes there are decimals with it. You don't need to know why. It has to do with the fact that sometimes atoms have different isotopes, which is it's the same element, but they have different number of neutrons in the nucleus. So anyway, now since if you have the number of moles times the grams per mole, that's going to give you the mass, because moles times grams per moles is going to cancel out, and you're left with grams. And so M, mass, equals number of moles times molar mass. Now if we substitute in, remember in this earlier equation we have mc delta T. If we substitute this for M, we get an mc delta T, right? And this mc here is called the molar heat capacity of whatever you're talking about. And instead of a small c, it is a large C. And so if we plug back in that big C for MC here, then we have Q equals NC delta T, where capital C is the molar heat capacity. Okay, now, final footnote here. Especially for gases, the molar heat capacity differs significantly whether you're measuring it at constant pressure or whether you're measuring it at constant volume. And usually for gases, you measure the molar heat capacity with regard to constant volume, because these two are going to differ a little. So if you're talking about a gas and you have a capital C for molar heat capacity, just assume it's the CV here, the molar heat capacity measured at constant volume. Now for solids, the specific heat and the molar heat capacity are usually measured at constant pressure. So in that case, if you just have a C and it doesn't tell you which it is, it's probably CP, the molar heat capacity measured at constant pressure. Who knew? Now, one last thing in this section. The rule of Dulong and Petit. On a per atom basis, it takes about the same amount of heat to raise temperature. It's about 25, I believe, is the molar heat capacity of most individual atoms, no matter what element it is, which shows us that specific molar heat capacity more has to do with the number of atoms than it does to do with what kind of atom it is. Well, I hope that was at least a little bit clear, this section on quantities of heat in Young and Freedman's University Physics.